Hey, you all, this is Andrew Franklin, Associate Professor in the Department of Psychology at Norfolk State University. Happy to be here with you all talking about hypothesis testing. During the course of this presentation, we're going to talk about different variables that you should be able to distinguish within the context of hypothesis testing. So we'll do some rudimentary review as it relates to independent variables, dependent variables, and extraneous variables. From there, we're going to segue into talking about examples of those variables, and we will slowly get to the point of talking about the 4 steps for hypothesis testing. In the midst of talking about hypothesis testing, we will also differentiate the different types of hypotheses that are present in any kind of scientific study, be it empirical in nature or otherwise, and then we'll work through some hypothetical examples and considerations that you need to give to results that you garner from the work that you do. So I hope that you get something out of this presentation, and without further ado, let's get started. For the first part of this lecture, we are going to take some time to review the definitions for certain variables. The first variable we will look at is the independent variable, also known as the IV. The IV is the variable that the experimenter is controlling. For example, if you wanted to indicate how long it took for a candle to burn, the independent variable would be the amount of time. This variable explains the changes in our next variable, which is the dependent variable. The dependent variable, also known as dV, is the variable that is measured and expected to change because of the IV. In our simple research example about how much time does it take to melt a candle, the height of the candle is our dV because it is dependent on the amount of time, or the IV. The last type of variable we have is the extraneous variable. This is any uncontrolled variable that may cause changes in the dependent variable. When research designs are set up, the idea is to minimize any risk of extraneous variables within the design. In our example about time it takes for a candle to burn, an extraneous variable would be the amount of wind in the area or oxygen levels. Both would have an effect on how long it would take for the candle to shrink. The following are examples of IVs and DVs. The first example is study habits and grades. Since one's grade depends on their study habits, the grade is the DV, or the variable that is measured and expected to change based on our IV being the study habits. The IV could be defined based on how long someone is studying or how they are studying. For example, are they reading notes or practicing flashcards? The next example is physical exercise and strength. Which one is the dependent value? How about the independent value? In this example, physical exercise is the independent value and strength is the dependent value. One's strength depends on how much physical exercise they engage in. How about the next example? Physiological symptoms such as blood pressure and heart rate and racist comments on TV. Which one is the dependent value? How about the independent value? The DV in this example would be the physiological symptoms, and the IV would be racist comments on TV. The idea is that the more racist comments on TV, the higher the physiological symptoms such as blood pressure or heart rate may be. Next, we have mindfulness activities such as meditation practices and degree of concentration. For this example, the degree of concentration would most likely depend on the mindfulness activity, making mindfulness the IV, and degree of concentration would be the DV. For the next example, maybe a therapist is working with a client who has social deficits or difficulties. For this example, the therapist is working on social skills education sessions to assist with the social deficits in hopes that the client may make more friends. In this case, which one is the DV and which one is the IV? If you said the number of friends is the DV and the social skills training is the IV, you are correct. The last example is very similar. The IV would be the Toastmasters membership, and the DV would be one's confidence with public speaking. So, next part of this presentation deals with us discussing what hypothesis testing is and why we need to do it. Hypothesis testing draws a general conclusion about a population by using data from a smaller group of people called a sample. Often it is impossible to test the entire population, so using a representative sample is the best way to make generalizations about the population. The process of hypothesis testing starts by stating a hypothesis about an unknown phenomenon or what we are investigating within a population. So the four steps for hypothesis testing are listed. These four steps include the following: state the null and alternate hypotheses. So it should be noted that in most peer-reviewed literature, you will process the null hypothesis usually is not laid out. It's something that the researcher has to disprove, and the researcher has to disprove it because in any kind of scientific investigation, conclusions that are generated are never definitive or absolute. Remember, these conclusions are all based on probability. So the scientist is going in with an inherent understanding that they have to disprove the null hypothesis. But again, keep in mind it may not be explicitly stated in the manuscript that you're reading or even voiced aloud if you're at a conference presentation listening to someone. The alternate hypothesis, which is typically the research hypothesis, is laid out. You will see that conspicuously written within the manuscript or stated out loud by a presenter at a research conference. The alternate hypothesis is typically what the researcher believes. Okay. So also in step one is selecting an alpha level. The alpha level is the probability of incorrectly rejecting a null hypothesis when it is indeed true. Locating the critical region. So critical regions are regions that are typically marked within the tails of a distribution that allows a researcher to determine when a statistical significance is occurring. So when they calculate a statistic, if it lands in shaded area in a critical region, right, which is the percentage that directly comes from whatever you decide in terms of your alpha level. So if you decide 0.05 or 0.01, then that would be like the percentage that would be in the tails of your distribution or tail of your distribution. This is the area in which you would be looking to see if certain scores fall in order for you to arrive at certain conclusions. Computing a test statistic is exactly what it sounds like. So this could be any statistic that exists that is designed to answer your research question, everything from a z-score to a z-test to a one sample t-test, an independent samples t-test, a paired samples t-test, a one-way ANOVA, a factorial ANOVA, which could be just for purposes of conceptualizing two-way ANOVA or a three-way ANOVA or a four-way ANOVA. All of those are factorial ANOVAs. It could be a multiple regression, a chi-square test, a structural equation model. So all of that would fall within computing the test statistic step. And then finally, the final step is to make a decision on accepting or rejecting the hypothesis based on how your calculated statistic score falls within critical regions that you have selected or you're looking at based on the alpha level that you are using. The plural form of hypothesis is hypotheses. Since we have two potential outcomes, we call them hypotheses. A single hypothesis is an educated guess based on prior knowledge, research, theory, and observations. We will always have two hypotheses for every situation. The first type of hypothesis is the null hypothesis, which could also be noted by a capital H with a subscript of O. The null hypothesis states that there will be no change, difference, or relationship between our variables when looking in the general population. Basically, the null is saying that our independent variable does not have an influence on our dependent variable. The alternate or alternative hypothesis, noted by capital H subscript 1, is the opposite. It states that there will be a difference, change, or relationship in the general population. The alternative hypothesis states that there is a significant relationship between our IV and our DV. For our example, we are going to identify if a new drug can help reduce symptoms of anxiety disorder. Ideally, we want to see if this drug will work for the entire population, that is, everyone in the world who has an anxiety disorder. Since it's impossible to test everyone in the world that has an anxiety disorder, we will use a representative sample of participants to test our new drug. The null hypothesis states that there is no difference between health anxiety symptoms of the population at large and those in our sample who have tried the new drug. The alternative hypothesis will state that there will be a difference between the two groups, being that the sample who took the new drug we are expecting will have significantly less health anxiety symptoms when compared to our population. In step 2, we set the decision criteria. The distribution of sample outcomes is divided into two sections. Remember that our null hypothesis is that there is no difference between our groups and they are very similar, if not virtually the same. Therefore, we can say the null hypothesis is likely true, or it is very unlikely that it is true. Next, we select our alpha level. There are certain criteria for a study that tell us what the alpha value is, but for now this will be given to you and it's usually 0.05 or 5%. This alpha level is also known as the level of significance. It is the probability value used to define the very unlikely outcomes. Next, we would determine our critical regions, which are based on our alpha level. So, for the purposes of this hypothesis testing lecture, we will talk about distribution of sample means and extremely low probability values within the context of a z-test example, okay? Based on what I was discussing in the previous slide, bear in mind that we're looking at the anxiety scores of a sample and we're comparing it to the anxiety scores of a population. Let's assume that we have the anxiety scores of the population and we know on average what those scores would be. And we're going to give a sample that we have under our survey some medication in hopes that it will reduce their anxiety symptoms. And then the idea is that we're going to compare that sample mean to that population mean. Okay, so we will talk about how to do that with the z-test as we move forward. But for now, let's continue to talk about locating critical regions with that context in mind. The set of potential samples is divided into those that are likely to be obtained and those that are very unlikely to be obtained if the null hypothesis is true. If the null hypothesis is true, our sample mean will be closer to the population mean. This means that there is not a statistical difference between the health anxiety of our sample and so those that took the medication and that of the population. Thus, the null hypothesis would be supported. If there is a statistical difference between the sample and the population, the mean will fall in the critical region as you see highlighted in the slide, and there will be an extremely low possibility that the null hypothesis is true. Okay, so within this distribution of sample means, I want you to bear in mind that the population mean is dead center. It's in the middle of the distribution, right? We got a normal bell curve in front of us. So population mean is in the middle, and if the sample takes the medication and they don't experience any difference in terms of their anxiety symptoms, then it's very likely that they're going to fall within the white area that extends from the lower left of this distribution to the upper right of this distribution. if the medication does have an effect, then it's very likely that that sample mean is going to fall out in the tails, the lower part of the distribution, hopefully the lower part, because that would indicate that anxiety symptoms have been reduced as a result of the medication. And that's a low probability value if the null hypothesis is true. All right, and just a word about the distribution of sample means. So the distribution of sample means is all of the possible sample means you could have if you selected various samples from the population and plotted those scores. And if you did that and you added up all of those sample means and divided by the total amount of those samples, then you would likely end up with the population mean. All right, so just a word about this distribution of sample means, because I recognize that some folks may be looking at this graph not really understanding what it even represents. All right, so the critical region, very unlikely outcomes for alpha zero point zero 0.05 is everything that falls below negative 1.96 and anything that falls above 1.96. Remember, the critical region is defined by the alpha level value. So z-scores are nothing but raw scores or sample means that are transposed into standard deviation units or standard error of the mean units. And the standard error of the mean is basically like a standard deviation, except for it's a standard deviation for means. Okay, so alpha level 0.05 is 5%. That's the amount of probability that we're willing to accept of incorrectly rejecting the null hypothesis. And in this particular case, we're taking that 5% and we're dividing it up and putting it into both tails of the distribution. We have 2.5% on the lower end, we have 2.5% on the upper end, and the z-score that represents 2.5% of the lower and upper half of a distribution is 1.96. So let me quickly kind of keep going and tie all of this together. So if we were to take a sample mean and subtract the population mean from it as it relates to anxiety scores, and then divide by a standard error of the mean, right, to get a z-score. If the z-score we calculate is at negative 1.96 or lower, then that would indicate that, hey, maybe the medication is making a difference on people's anxiety symptoms and it's causing there to be a significant decrease of symptoms. If we were to do a different score between anxiety mean for the sample and anxiety population mean and transpose that into a standard deviation unit, and we ended up with a z-score that was positive 1.96 or positive 1.97, 1.98, etc., then that would still indicate that the medication is having an effect. We have a significant finding, and that the sample mean is statistically significantly different. A lot of leads there from the population mean. Okay, but it would be in the direction that we are not hypothesizing. All right, so this would indicate that actually the medication is causing an increase in anxiety symptoms. So I'm hoping that folks are seeing how all of that works. Step 3, collecting data. Our third step is to collect the data. Data is always collected after the hypotheses are stated and not the other way around, because you want to avoid biases that show up when you analyze data preliminarily and then generate hypotheses. The data is also collected after the decision criteria, step 2, is established. This makes sure that the research study is not biased and the criteria wasn't skewed to support any findings. The second part of the third step is to compute the sample statistic. This is done using the data that is derived in the study. In this case, we're talking about a z-score. All right, the second part of the third step is to compute the sample statistic. This is done using the data that is derived in the study. Computing the sample statistic, in this particular case, a z-score, will show the exact position of the sample as it relates to our population. In other words, z is the difference between the observed sample mean and the hypothesized population mean divided by the standard error of the mean. So, for the purposes of the example we've been discussing, we would be using this z-score, and we would already know our population mean. We would have an idea of what the standard error of the mean is, which, keep in mind, is like a standard deviation unit. It's just the average dispersion that we would expect amongst a distribution of sample means around this population mean. And then we would have the sample mean, which would be the average anxiety scores that we calculated after participants tried the new medication. Okay, and so we would do this statistic. We could do it by hand, or we could do it in SPSS, and it would give us a z-score, and then we would take that calculated z and see if it falls below negative 1.96 or above positive 1.96 based on our 0.05 alpha level, and that's how we would determine if the medication was having a significant impact. Okay. Now, just for the sake of going over the different z-score tests, I included these two as well. So this is a z-score formula as well. In this particular case, you have X instead of the capital M, which represents a population mean. So you have X, you have mu, which means population mean, same as the one that's listed here, and then you have this lowercase Greek symbol, which means standard deviation unit. So if we were outside of the example we're talking about, if we were to use this z-score formula, we could determine where a raw score falls standard deviation wise within a distribution of raw scores. Okay, and this is specifically to be used when you have a raw score that is coming from a population, because these Greek symbols represent populations. Over here, all of this is indicative of work being done with samples. So we have X, which is a raw score. We have X bar, which means sample mean. Keep in mind, this means population mean. This means sample mean. Then we have a lowercase s, which means the standard deviation of a sample, which is different from the standard deviation of a population or the standard deviation as it relates to a distribution of sample means. Okay. And you could use this z-score formula here to determine where a raw score falls within a distribution of raw scores from a sample. Okay, so in some of the assignments that you may be doing for the course, you're tasked with calculating z-scores in SPSS or by hand, and you can do both, and these are really useful. Oftentimes, practically, researchers use this to determine if raw scores are outliers, and if they are outliers, are they justifiable outliers? Should something be done with them? Like, it's important for us to be able to identify if we have outliers within our data set, because ultimately those can have an effect on other statistics that we run with our data, be it basic statistics such as measures of central tendency or measures of variability, or even the more advanced ones. So outside of this lecture, when you think about z-scores, think about them being useful in understanding certain scores within your data set, or understanding your means within a data set, and identifying outliers. Okay, and for kind of bare bones, more preliminary research, you can also use them like we're doing here to determine if there are significant differences present within your data set. Step 4. All right, step 4 deals with making a decision. The fourth and final step is to make a decision. We will always make our decision based on the null hypothesis. We will either reject it, meaning there is a statistically significant difference between our groups, or fail to reject it, meaning there is not a significant difference between the groups. If the statistic, the z-score, is found in a critical region, we reject the null hypothesis. If the sample statistic calculated in step 3 is not located in the critical region, it falls closer to the population mean, we fail to reject the null hypothesis. The decision is never based on the alternative hypothesis, always the null. So just to recap a few things, remember with the null hypothesis, there is no change or difference between the treated population and the general population, specifically as it relates to our example. This must be disproved to support a treatment. With the alternative hypothesis, there is a change or difference between the treated population and the general population. This is commonly found to be what the researcher believes or is trying to support. With hypothesis testing, it also bears to consider that we have two types of error that are possible. These are called type 1 and type 2 error. Type 1 error is rejecting the null when we should not have. For example, the null hypothesis is true. This is also known as a false positive. Type 2 error is retaining the null, when we should not have. In other words, the alternative hypothesis is true. This is also known as a false negative. A pregnancy test is a great example to demonstrate type 1 and type 2 error. Let's say a couple is trying to have a baby. Let's say the wife takes a pregnancy test and it shows up positive that she will have a baby, when in actuality she is not pregnant. This is called a false positive, also known as a type 1 error. Let's say that she takes a pregnancy test and the results show that she is not pregnant, when in actuality she has a baby gestating inside of her. This is called a false negative or a type 2 error. All right, so remember, type 1 error is rejecting the null when we should not have. That is, the null is true, also known as a false positive. This supports that it is highly unlikely that our sample came from our population, yet not impossible. Type 2 error is retaining the null when it should not have been. That is, the alternative hypothesis is true or a false negative. This could arise by getting a sample that was uncharacteristic of our treated population. So I'll conclude with this slide, which deals with some concerns and some thoughts about measuring something called effect size. Although commonly used, some researchers are concerned about hypothesis testing. Many believe that the focus of the test is data and not the actual hypothesis. Others believe that significant effects are not always substantial or practical effects. In other words, they could be occurring due to extraneous variables and not the IV having a direct effect on the DV. Statistical significance does not always equate to practical significance. And this is where effect size comes in. If the null hypothesis is rejected, we can measure the effect size. Effect size measures the absolute magnitude of a treatment effect independent of sample size, because typically as sample size increases, there's a higher probability of you finding a significant effect or a significant difference as it relates to your study variables and overall your data. So a type of effect size, Cohen's d, measures effect size simply and directly in a standardized way. And I just want you to be aware that there are these different tools out there that more directly get at the impact of IV influencing dependent variables. Well, I hope that this presentation was helpful. If you care to, feel free to comment, like, subscribe, and for my students, if there are any lingering questions, feel free to field them my way. Take care.